Alright guys, make sure you have your notebook out and your data booklet open to page 9. This is topic 9.3. We're dealing with double and more multiple slit interference. So for this video, we're only looking at this first equation. This equation is good for double slits, diffraction grates that have thousands of slits. N is the order of the maximum. So N is equal to the order of the maxima. So that's the number of peaks beyond the central peak for an intensity or an interference pattern. So this would be if n equals 0, this is where n equals 1, n equals 2, n equals 2, n equals 3. So 1, 2, 3. You count the peaks on either side of the central max to give you the n. Lambda, again, the wavelength of light. D is the distance between the slits, and sine theta, or theta, is the angle between the central maximum and any subsequent maximum. So that angle subtended. So again, between here and here, or here to here, or here to here, it's that angle between the center of the central maximum and the center of the subsequent maxima. So hopefully you can see I'm trying to draw this as well as possible. Okay, and then the other two equations, we will cover in the next video. They are for thin film interference. So here we go, blast from the past. If you guys remember the double slit interference pattern that we saw for topic 4, remember double slit interference with light waves was explored by Thomas Young. What this experiment showed was that yes, light is indeed a wave, what many people thought. It has wave-like behavior. You have the wavelength of light and it's incident on a double slit. The lowercase d is the distance between the slits. The waves spread out through two openings, and each of those openings become their own source of light, where you have the distance from the slits to the screen, capital D. And then you have the maxima. N equals 0 is where you have the brightest intensity, the central max. N equals 1 are the subsequent maxima, and you have what's called the fringe spaces, the S, which is the distance between the center of the central maximum and subsequent maximum. So the following formula, as you may recall, this is topic 4.4, relates wavelength lambda, slit separation, lowercase d, and distance, capital D, to the screen, to the separation S of the maxima. We derived this last year using the small angle approximation. So S, the fringe spacing, is equal to lambda big D over lowercase d. This is a neato animation which just shows water wave behavior as it diffracts and interferes through two openings. Again, where two crests meet or where two troughs meet, there is constructive interference. So for water waves and for light, you have the crest would be here and a trough would be here. And so when you have two crests meeting and two troughs meeting, that's constructive interference. These waves are totally in phase. But if you have a crest meeting a trough, these are out of phase by a full pi, 180 degrees, and so there is destructive interference. You get a flat line. So the waves would just cancel out. For water waves, you wouldn't have either a crest or a trough, the upper part of the wave or the dip in the wave. You would just have a flat, smooth surface. For light, what you see is a dark spot. There is no light there. The electric part of the field is gone, but the magnetic part of the EM field is still there. We don't need to know that. In this case, for constructive interference, you get a brighter or a taller wave, the superposition of the two. You would see along all of these lines are where you would have constructive interference, where you would have a crest or a trough. And again, the S is the fringe spacing. So here is where we need to expand on our understanding from topic 4. We now know that a single slit causes waves to interfere. You get an interference pattern from a single slit. So because in the double slit experiment you have two single slits, each single slit modulates the intensity pattern of, or the interference pattern of the double slit. So there's something called modulation, is what you're seeing. The bottom image shows what the double slit pattern actually looks like. We still have regular separation S, but the intensity varies. The top image shows the interference pattern from the single slit. So this is the same pattern, but one of the slits is blocked. So the single slit intensity envelope determines the double slit intensity pattern. So what do I mean by the single slit envelope? Well, if the double slit intensity were not modulated by the single slit effect, this is how the double slit intensity pattern would look like. You would just have a series of all of these peaks. They would all have the same intensity no matter what the end value was, no matter what maximum you're talking about. This is what a two-source interference pattern looks like. But because of single slit constructive and destructive interference, we know that according to Huygens' principle for waves, every point in the wave acts like a little wavelet, so the wave coming through a single slit can actually interfere with itself because of all of those little wavelets making up the wave. Because of this single slit interference pattern, the actual double slit intensity looks not like this, a series of peaks, but like this. The double slit interference pattern is modulated by the single slit, by two of those individual slits. Double slit intensity, single slit intensity. Notice the center part of the double slit intensity pattern fits within the space of the single slit intensity pattern. This is called the single slit envelope. This is what they mean by the single slit envelope. So what you see with the double slit pattern, it has many, many more peaks, but the overall shape of that intensity is quote unquote modulated within the single slit envelope. Modulation is a very important concept for AM and FM radio waves. So incidentally, the overall double slit intensity of the brightest portions of the interference pattern are actually brighter than just the single slit pattern. That should make sense. If you have more slits open, the brighter that pattern is, or the more light comes through. It turns out that if N is the number of slits and I1 is the intensity of the single slit central maximum, this is the single slit central max, then we can get this relationship for the intensity of the central maximum for N number of slits. This equation isn't in your data booklet, but it might just be helpful if you kind of have this equation in the back of your mind, because they do ask questions on how the number of slits, having multiple slits open, changes the intensity pattern. So I sub n is equal to n squared times the initial intensity. I think as long as you know increasing the number of slits increases the intensity, the brightness that you see, it should make sense. You might not need to memorize this equation. So using that equation from topic 4.4, the separation between the maxima, S, the fringe spacing, is given by lambda capital D divided by D that we calculated for two slit interference, shows that the location of the single slit envelope peaks for multiple slits separated by D is illustrated like this. You can see that as you increase the number of slits, you are still having like this central area for all of these interference patterns that pretty much has like the same width as just like a single slit interference pattern. What you have are still the fringe spacing between the primary maxima is the same. So the primary maxima being the largest intensity patterns on the screen. So these are all the primary maxima. And then in between those primary maxima, what you see is as you increase the number of slits, you get a bunch of little secondary maxima, these smaller dots. They get harder to see as you increase the number of slits, but they're there. Sorry about that. Okay, the intensities for 1, 2, 3, and 4, 1, 2, 3, 4, and 5 equally spaced slits are shown here for part of the central maximum envelope. So here we have the single slit, the very broad central maximum. For the two slit, you have modulation of that intensity pattern. You get more primary maxima within the broad single slit envelope. 3 slits, you can see 3 large peaks within the broad central maximum. 4 slits, 5 slits. You can see those smaller secondary maxima in between, but all of this is modulated within that single slit envelope. Note that the double slit separation, S equals lambda D over D, remains the same as you add these peaks. The fringe spacing, the S value, is the same. The center of these primary maxima does not change. Also observe that the intensity increases with the increase in slits. As you increase the number of slits, more light gets through, the brighter that intensity pattern is. So diffraction gratings, as you might remember, are used to make the optical spectra. You use diffraction gratings to analyze chemicals, the chemical signature produced when you heat up gases, or the chemical signature absorbed, or the light absorbed by any compounds. What helps you analyze this light is diffraction gratings. They're analyzers. So if you try to analyze white light with a diffraction grate, you allow that light to shine through a diffraction grate, you see this pretty rainbow spectrum. It's a continuous spectrum. White light is made up of all of these beautiful colors. Now, if you have, for example, a cool gas made up of some or more elements, maybe some molecules, and you shine that light, you shine light onto that cool gas, what you see is the absorption spectrum. If you look at that light, that's allowed to pass through the cool gas using a diffraction grate, you look at that gas's absorption spectrum. There are missing wavelengths from the continuous spectrum. That's the energy that gas can absorb. Compare that absorption spectrum with the emission spectrum. Hot gases can give off light. If you analyze that light with a diffraction grate, you see the inverse of the absorption spectrum. You see the wavelengths of light that gas emits. So don't forget about this stuff, because as we go into topic 12, we're going to bring this information back. But diffraction grating makes it possible to analyze gases and to analyze light. So just as a reminder, a diffraction grate consists of a large number of parallel equally spaced lines or grooves etched into glass or some plastic substrate through which light passes or gets reflected. So this is just a picture of a spectroscope, kind of like the ones we have in class, and this is a picture right here of a diffraction grate. So the diffraction grate has these dark lines where the light can't pass, and then it has these spaces, these opening slits where the light can. So different wavelengths are diffracted at different angles, producing interference maxima at angles theta, given where n is the order of the maxima. N equals 0 is where you have the central maximum. It's the one in the center. N equals 1 is on either side of the central maximum. N equals 2 on either side, etc. So we have this equation, n lambda equals d sine theta. This is the diffraction grating maxima locations. It works no matter how many slits you have, 2, 3, 4, up to thousands, thousands of slits. Okay, n is the order of the maximum. D is the distance between the lines, the spacing between the slits. N equals 0 is for the central maximum. n equals 1 on either side of the central maximum, n equals 2 on either side of the central maximum, and the angle incorporates only half of the pattern. So the angle theta is from the center of the central maximum to either n equals the center of n equals 1 or the center of n equals 2. So this angle just incorporates only half of the total angular dispersion of the image or of the interference pattern. Here we go, question number 1. In a double slit interference experiment, the following intensity pattern is observed for light of wavelength lambda. The distance between the slits is little d. What can be deduced about the value of the ratio lambda over d and the effect of single slit diffraction in this experiment? So do we see that single slit modulation? I think we do. If we didn't, we would have, remember, a series of peaks, all the same height, just a bunch of them. But what we do see, in fact, is the modulation of the double slit pattern in the single slit envelope. So there is a non-negligible effect of the single slit diffraction. So we are going to get rid of two choices C and choice D. Now they want to know what the ratio lambda over d is. So if I use the equation n lambda equals d sine theta. If you're not, so we're looking for the angle here. Sometimes it is possible to use the small angle approximation where sine theta is approximately equal to theta. In the case of this, where you have a really tiny number of rads, I think it's when, I remember correctly, it's like less than 0.02 radians, it's less than 10 degrees, so whatever that is in rads. You can use the small angle approximation where sine theta is approximately equal to theta. And if you don't believe me, you can change your calculator to radians and test some of these angles here. And what you'll see is sine of these angles approximately equals just the angle itself. So it's a very handy technique. So in this case, what we're looking for is the ratio lambda over d, and I'm going to assume sine theta approximately equals theta, so I have n lambda is equal to d theta. So lambda n times lambda over d should equal theta. If n is 1, this ratio becomes just lambda over d. So for n equals 1, that would be this peak right here. And we just need to figure out, okay, what is the angle between the n equals 0 and n equals 1? So I just have to look at the graph. Okay, this is 0.02, so this has to be 0.01, 1 over 100. In this case, lambda over d, 0.01. It's that easy. All right, question number 2. Light of wavelength lambda is incident normally on a diffraction grating that has a slit separation of 7 lambda over 2. What is the greatest number of maxima that can be observed using this arrangement? So we'll use the equation n lambda is equal to d sine theta, and we're going to solve for the number n because n will tell us the subsequent maxima beyond the central maxima, the number of those that we have, and then if we do a count on both sides of the central max, we should get the full number of maxima. And they're asking for the greatest number. So the greatest number of maxima can be seen when sine of the angle is 1. So obviously sine theta is a max at 1. That's where you'd see the maximum number. So n times lambda equals lowercase d. We're going to look for this number n. So n lambda is equal to 7 lambda over 2. Lambdas cancel, and you have n equals 7 over 2. You're never going to see part of a peak. You have to round this number, this n, down to the nearest whole number. 7 over 2 is 3.5. So in truth, you see 3, n equals 3 peaks beyond the central maximum. So if I draw a graph, or the intensity pattern, this would look like my intensity pattern. The middle here is the center, and you see 1, 2, 3 peaks. You round down to the nearest whole number. But I know that this double slit or this diffraction equation is good for only half of the interference pattern produced. So on the other side, you would also see n equals 3 peaks. That is a total number of 1, 2, 3, 4, 5, 6, 7. 7 peaks. It might make sense to you to say, okay, we could have just doubled 7 over 2 lambda, but I want to make sure it's clear that you round down to the nearest whole number, because in other problems where this isn't such a nice half, you still need to round down to the nearest whole number for the n value. And just to remind you what incident normally means, the normal line is 90 degrees with respect to the surface. So if we had a diffraction grate here and it's incident normally, the light here could be in yellow. That means it's striking the diffraction grate at a 90-degree angle. That's normal to the surface. So question number 3, a beam of monochromatic light is incident on a diffraction grating of n lines per unit length. The angle between the first orders is theta sub 1. What is the wavelength of the light? So this question is a lot like question number 2. This angle is between the first orders. So what this angle is showing us is this would be the subsequent maximum right here, the central maximum here, and then the subsequent maximum here. So the angle, rather than just incorporating half of the interference pattern like it should, it's incorporating the full pattern. So if we're gonna use this n lambda equals d sine theta equation, this theta sub 1, we need to halve it. So this becomes n lambda is equal to d sine, open parentheses, theta sub 1 over 2. You would half this total angle to get the angle theta. Okay, and n in this case would equal 1, because that's the maximum that it's landing on between the first orders. So the order is n equals 1. This equation then further reduces to lambda is equal to d sine theta sub 1 over 2, and all we're left with is to figure out what the lowercase d is. So diffraction grates are typically labeled with n lines per unit length. So to get the little d value, to find out what the spacing is between those slits, d would be the length, the unit length divided by the n number of lines. So you take this number and you invert it. So it's 1 over capital N. In that case, the only choice then, choice D. All right, light of wavelength 700 nanometers is projected normally on a diffraction grating ruled with 500 lines per millimeter. The number of diffracted maxima is n lambda equals d sine theta. And because we're looking for the total number, we go with the angle being the maximum dispersion. It's a maximum possible value of sine theta is 1. So n lambda equals lowercase d. We're going to solve for n. N is equal to d over lambda. And the grate has 500 lines per millimeter. This is 500 divided by 1 millimeter, or 1e negative 3 meters. So to get the lowercase d, you need to invert this. So the lowercase d, 1e negative 3 over 500, divide by the wavelength of light, 700 e negative 9, and you get the order of the subsequent maxima as n equals 2.857. Now remember, like from problem 2, you round this number down to the nearest whole number. You don't see a full 0.857. What you see is a total number of 2, n equals 2 peaks. And that's on either side of the central maximum. So again, if I sketch this intensity pattern, you'd have n equals 0, whoops, n equals 0, n equals 1, n equals 2. But you have that on both sides, n equals 1, n equals 2. So the total number of peaks you see, 1, 2, 3, 4, 5, 5 peaks to this diffraction pattern. Question number 5, last one for this video. Orange light with a wavelength of 590 nanometers is shown upon a diffraction grating. What is the maximum number of slits per millimeter to produce 19 principal maxima on a screen? So if you remember from all the patterns I've been drawing, what you see is about half of the pattern. You have n equals 1, n equals 2, all the way. Okay, so if we're seeing 19 principal maximum, we're seeing the central peak and we're seeing equal numbers of peaks on either side. So to get the n value from this, you need to take this number, this 19, you subtract out the number of central peaks or the primary maximum, the central maximum, subtract that out. That gives you 18 peaks on either side of the central maximum. 18 maxima on either side of the central maximum. So to figure out how many are on either side of the central maximum, just divide by 2. 18 over 2, so the n is equal to 9. That angle is coming out all the way to the 9th peak. And that is the total number you see. So if you use the equation again, n lambda equals d sine theta, and we are at the full spread of the angle, so sine is 1. That equation becomes n lambda is equal to lowercase d. Take 9 times 590 e negative 9, and you get a value for the lowercase d as 5.31 e negative 6. Okay, but they want the maximum number of slits per millimeter. Slits per millimeter, and this is in meters, you need to invert this number. So we will do 1 over 5.31 e negative 6, and this will be in per meters. So raise that answer to the negative 1 power, and you get 1.88, clear up some space here. The total number of lines per meter, the lines per meter, equal to 1.88 times 10 to the 5 E5 lines per meter, but they want per millimeter. So you will divide, you know that in every 1 meter there are 1,000 millimeters. So you'll divide this number by 1,000, or you can subtract 3, because this is 10 to the 3rd. You can take away 3 from here, so this becomes 1.88 E2 lines per millimeter, or 188 lines per millimeter. Alright guys, thanks for watching. If you need, check out the Cognity, I think it's 9.3.2. It's on diffraction and double slit interference, and we'll do the thin film interference next time. Thanks for watching.